Thank you. So let's get started. Thanks for joining me today. I'm Rustin. Today I'm going to talk about the TiDB Analyze feature. It's a feature that collects the statistic for the optimizer to generate the query plan. It's based on the cost model, right? All my example and the algorithm are based on the TiDB version 0.1. So if you want to take a look at the source code, you need to make sure you are on the 0.1 tag. All right. So let me introduce myself. So I just transformed to the optimizer team about 1 year ago, and I'm also very active in the Rust community. So if you have any question about the Rust toolchain, feel free to reach out to me. We can discuss it together. This is today's agenda. We'll start with an overview of the Analyze feature with some examples. Then we'll dive into the data structure and the data flow overview. We'll take a look at the data structure and the data flow from both TiKV and TiDB perspective. Finally, we'll have a Q&A session. If you have any question, feel free to send it to the chat box. I'll take a look. If I can't answer your question, probably Kunqing, Yiding, or Terry, you can help me answer those questions. So first, we'll take a look at the Analyze feature itself. There are some Analyze statements here. The first one is about the Analyze tables, right? It's pretty common, and you can specify multiple tables in one single Analyze statement to analyze. For example, right now we are trying to analyze table T1, T2, and also for the partition table, you can specify which partition you want to analyze them, right? At the same time, you can specify which specific column you want to analyze. As same for the indexes. Also, you can combine them together. Like here, we try to analyze the column C1 and C2 for the partition P1 from the partition table T. It's same as the indexes. And there is a special syntax called analyze table T with the predicate columns. That means if you try to execute this statement, we'll grab the column columns that we used in previous query and take it as a predicate column. Like if you use a column in your where clause, we'll take it as a predicate columns and analyze those columns. Because usually for the OLTP workload, we only use few columns in our where clause or group by or order by clauses. So we don't need to analyze all those columns from the whole table. We just need to analyze a few columns. Most of them have some indexes. So this is a really good feature to help you reduce the resource consumption from this analyze statement. Finally, you can also specify some options about how many statistics we'll collect for this specific table. So here we only want to grab 20 TopN for this column C1 and C2. So you can specify the options here. After we executing the analyze statement, we'll generate some statistic from the TiKV. So in this section, we'll examine the data structure used to store this statistic. Let's start with a simple example. First, we'll create a table named T with a single column A here. Next, we'll insert 2,000 rows into the table. And notice that we insert the same value twice for every even number here. So please keep this example in mind because we'll use it later to demonstrate the data structure. So this is how what's data distribution of this table. Let's take a look at some simple queries. So in this query, we select rows where column A equals to 100. This is a basic example of a column selectivity using a simple equality condition. The optimizer estimates there are 2 rows that match this condition. From the code, if you take a look at the code base, you'll find out that it uses the TopN data structure to make this estimate. because the value is in the TopN data structure. Because for TiDB, we collect almost on version 8.1, we collect almost 500 TopN values. So 100 is definitely in the TopN data structure because it's a even number, right? So we inserted twice, so the estimate is 2, right? Under the hood, we use a system table called stats TopN to store the TopN data structure. If we query this table, we can see the TopN values and their counts. So this is value and this is count. For example, you can see the first value in this TopN table with a count of 2. So it means for this specific value, it's a 0, right? We have a 2 0 in this table. Because in our example, the data skew isn't very high, so all values have the same count. But in reality, this would be the top 500 values from your table. It will tell us about the data skew, right? Now let's take another look, because we hint that 100 in the TopN data structure, but this time we selecting rows via column A equals 1999, right? Since we only collected the first top 500 values, the value isn't in the TopN because this almost is the last value of the table, right? So in this case, the optimizer uses a histogram to estimate the number of the matching rules. The final result is 1. So the optimizer estimates that only one row matches this condition. The reason is that the value 1999 is in the histogram, and we hinted, so we matched it. I'll show you the histogram data structure in the next slide. Basically, we just hint this value in the histogram, so we know exactly how many values, how many repeats of this value in your table. Same as before, we use another system table called stats buckets to store the histogram data structure. If we query this table, we can see the histogram bucket here. In this example, we can see for the first one, the value 1999 is in the histogram bucket with a count of 1. So the counted 1 and the repeat value is 1. So we've hinted this value and we can estimate they are exactly one row match that condition we saw before. And if we take a look at the next one, the lower bound and the upper bounds of this bucket is 1993 and 1998. Additionally, the repeats are 2, means there are 2 repeated value of the upper bound. This is very special because we only record the repeats value for the upper bound. So it's kind of a special TopN in histogram. So because for other data located in this range, we don't really count the repeats. But for the upper bound, we do this kind of specialized stuff. And we can use this repeats when we try to do some equality condition estimation, right? So if you take a closer look at the histogram buckets, there are some fields of this data structure. ID is pretty simple. It's just a unique ID for the histogram bucket. And the count is the number of values till the bucket. So this is a cumulative count, including all values up to the bucket. But when we store the data, we only store the count of a bucket, because during we load those buckets to the TiDB, we all do this kind of calculation to get a cumulative count, because we all use it when we do the area estimation. The number of repeats is the number of repeated value for the upper bound. It's a special case. It's more like a special TopN in histogram. And we have a lower bound and upper bound. And the last one is pretty special. We in the past, we tried to collect the NDV, aka number of a distinct value. So but we failed because the accuracy of this field is not very good because we use the samples from TiKV to build our TopN and histogram data structure. So the NDV is not good enough. So we decided to deprecate it. And right now it's always 0, as you can see. So if we take a look at this, if we break down the content repeats, as you can see, we just have those values in this bucket in this specific range, and the repeats value is just for the upper bound, right? As you can see, if you just like grab all the histogram buckets from TiDB, and you can see this graph. We use a equal hat histogram to store the data to build up our histogram. The reason we use a equal hat histogram is that it provides a more accurate estimation of the selectivity of the column compared to the equal width histogram. If you want to know why it is more accurate, you can find more information in this paper. The whole paper is about how to estimate the number of tuples satisfying a condition with a equal histogram instead of a equal width histogram. It has a lot of details about why we choose equal histogram. So take a look if you are interested. Now let's look at the last example. It's also very simple query. This time we are selecting rows where column A equals to 9999, right? Since the 9999 isn't in the TopN data structure and the histogram data structure, because we only insert 200 rows to this table. So 9999 is definitely not in the TopN data structure and the histogram data structure. The optimizer uses a different method to estimate the number of matching rows, as you can see here. So in this case, the optimizer uses a null count. Here, optimizer uses a null count and NDV to make this estimation. So I'll explain what is NDV and what is null count and how we calculate them. The null count is pretty straightforward, right? It's just a number of null values in the column. We can easily get this information from TiKV because we know which value is null and which value is null, right? But the NDV number, aka number of distinct value in the column, it's really hard to tell, right? Because even you scan the TiKV, we need to find some way to get this NDV distribution, right? So to calculate this NDV, we use a FM sketch algorithm. This algorithm provides an efficient way to estimate the number of distinct values in the large data set. So, but before I dive into the details of the algorithm, let's take a look at the data flow from the big picture. Let me grab some water. So this is a data flow overview of an Analyze feature. So first, the TiDB owner or client executes the analyze statement, because for the TiDB owner, we need to do some auto analyze for users, because we don't need we can't ask the user try to analyze the table or ask the DBA to analyze the table again. So we need to do some automatic work to help them to reduce the burden of maintain those statistics. So basically, first the TiDB owner or clients executes the analyze statement. Next, the TiDB sends an analyze gRPC request to TiKV, and the TiKV will collect those statistics and send them back to TiDB. Finally, the TiDB will grab all the statistics we get from the TiKV and build and merge the statistic. Build the TopN data structure and build the histogram data structure and updates those statistics to the system table, right? We actually, during this process, we use the same coprocessor framework to collect the statistic. This is a special request handled by the coprocessor. So basically, usually, we can use a SQL interface to calculate the TopN and to calculate the histogram, but we didn't, because at that time we decided to use a special request to do this analyze work. But maybe in the future we can have some improvement to use a common cool interface instead of have some special request to TiKV. I won't get into all the details of how we reuse this coprocessor framework to do to collect the statistic, but you can find more information in TiKV repository under the coprocessor V1 or V2, maybe V1. We still have that special code for the statistic for the analyze statement. All right, so in TiKV, we only do two things. The first one is calculate the FM sketch. We scan all the data to calculate the FM sketch because we want to have an accurate NDV because it's so important to the query estimation. So we need to go through all the data from one table and calculate the FM sketch, I mean the NDV number. And also we do sample the data because we can't send all the data back to TiDB. That's becomes like a full table scan. It's terrible, right? So we need to do some sampling here. So before we dive into details of the FM sketch implementation, let's take a look at the mathematical assumption. So first, we assume that there is a hash function, and those hash functions are independent. This means that's a hash function hx that uniformly distributes the input elements over a large range of integers. So basically, we map each input to a random integer, right? Second, we assume that the number of trillion zeros in the binary representation of the hash value follows the geometric distribution because we just map them to the random binaries. So we can check its trillion zero and assume they follows the same distribution, right? These assumptions are critical for the accuracy of FM sketch and how it works. So if you want to learn more about the FM sketch algorithm, you can find the original paper in the footnotes here. There are a lot of mathematical formula in this paper. I have to say I don't really quite understand them. So please don't ask me the mathematical questions. About the algorithm, we just use a hash mapping method to map each element of the set to an integer using a hash function hx. And for each hash value, we'll count the number of trillion zeros in its binary representation. So we basically check how many trillion zeros in its binary representation and record the maximum count R. And to do the cardinality estimation, we use the maximum trillion zero count R to estimate the cardinality of the set with a formula 2 to the power R. So we use this formula and to do this kind of a calculation. Maybe it sounds very complex or not very straightforward. So I will show you a simple example to demonstrate how it works. So if you click this generate hash value button, after we clicked this button, we can see that's the hash value and the trillion zero for each element. So this is it's a hash value, right? And this is how many trillion zeros of each element. So you can see the maximum trillion zero count is 4 from this element, right? So the estimated cardinality is 16. We use that formula from the paper. So this is a perfect example, right? As estimated cardinality matches the actually length of this data set. It's a 16. It's perfect. But in practice or in reality, there will be some case where the estimation is not as accurate because we sometimes will have some outlier in our database or in our table, right? So this time we have an outlier in the set. We have this value. It's definitely an outlier, right? If you click this generate hash value button, you can see this outlier has 6 trillion zeros. So the maximum trillion zero is 6. And the estimated cardinality is 64. It's definitely wrong, right? Because we only have 16 values here. this example, this is an example where the FM sketch algorithm doesn't provide an accurate estimation. So to address this issue, we need to use a multiple hash function to take the median estimate and combine them together and try to get a more accurate result. This approach proposed from that paper. So basically, you need to have a bunch of hash function and put them into the different groups and use the different groups to calculate the different hash value and count all the trailing zeros and try to combine all of the results and get a final cardinality estimation. But you can get that it's quite expensive, right? You need to have a multiple hash function. It's difficult to find some good hash function, right? So also you need to scan the data multiple times because you have a bunch of hash function and calculate the hash value multiple times. It's inefficient. So we don't really use this method. Even in TiDB codebase, we call it FM sketch, but it's not the original FM sketch. We use another solution. We picked a solution called a distinct sampling to solve this problem. So to address this issue, we use a new algorithm called a distinct sampling. The core principles of distinct sampling are follows. First, we use a hash function. It's pretty similar with the FM sketch, but this time we give it a fancy name. We call it die level. Basically, we use the same hash function, maps each distinct value to a random die level. And we maintain a sample S of a distinct value and a current level L. Keep values in S, and only if their die level is greater than or equal to L, I mean the die level L. So the estimation becomes we use the length of this sample dataset multiplied by 2 to the power L. So from this part, so basically we use a hash function to match each distinct value to a random value and check its binary representation to determine the die level. It's just the same as the FM sketch. So if there are no trailing zeros, the die level is 0. If there are 1 trailing zeros, the die level is 1, and so on. So it's pretty straightforward, right? If you want to take a look at the more detailed full concept of this algorithm, you can take a look at this paper. It's very good paper and easy to understand because they don't put too many mathematic formula in the paper. So if we want to implement this algorithm, we'll start with level 0 and an empty sample data set S. And for each row R, we just try to get the attribute value V and compute the die level to this hash function. If the die level is greater than or equal to level L, we'll put it into the sample data set. And at the same time, if the size of the sample set is greater than key, is another number we specified. So we'll increment L and remove the elements of the die level less than L, right? So this is a sampling part of this algorithm. So we only keep the items with a die level greater than or equal to L. Also, we keep control the size of a sample, because if you include all the samples, that becomes a table for scan, right? It doesn't make sense. Also, from this part, this is a key point to solve the problem of FM sketch. This means for the lower die level, we have enough samples to prove that the values follows this distribution or follows this pattern. So if you specify a really big sample size, you can get more accurate estimation. In TiKV, right now we use a really big value. I don't really remember the specific number, but it's quite big. So let me show you how it works from this simple animation. Okay. So every time if you click this next button, we'll process a new row. I mean, process a new column, right? This time the sample size is 8. So we'll increase the die level when the sample size is bigger than 8. If you click this button, we'll go through them one by one. And as you can see, this time we use a different hash function because I asked AI to help me generate this demo. So the AI picked another hash algorithm. So if you process the next one, we'll increase the sample size because we put all of them into the whole data set, right? Because right now the data level is 0. And it doesn't have any 0, but because the data level is 0, it's equal to 0. So we put it into the sample data set, right? And we keep going. And right now, we almost reach our sample size, right? This time, we reach our sample size. So after edge, we just increase our data level to 1. And only contains those values that meets this like a data level. So you have to at least have one in 0. Then we'll put it into the sample set. Otherwise, we'll dream off all those other values. So this time we only have a CD and the HI in the sample data set. And the estimated NDV is 8. And we keep going. Finally, we finished all the sample from as maybe TiKV. And the data level is 1, and the current sample size is 8. So the final estimate is 2 times 8, right? Because data level is 1. So the final estimated ND is 16. It's great, right? Because we only have 16 values here. Even we have an outlier here, but even we use the same hash function, if there are 6 hidden zeros here, we still can handle this kind of case, right? Because we don't change and we don't change our data level because it's all layer. So data level is still 1. So the estimation gonna still be the 16, right? So this is how it works. And if you are interested in this algorithm, you can literally jump into the FM sketch data structure from both like a TiKV code base or TiDB code base. They are using the same hash function and they are using the same data structure to do this kind of work. So this distinct sampling algorithm provides a more accurate estimation because it can tolerate the outliers, right? This algorithm provides estimates within 0% to 10% relative errors. And I remember I asked Yiding, in the most cases, our current solution, I mean, this algorithm is good enough. And for most cases, it's really accurate. And the algorithm also is very efficient, right? Because it only requires a single pass over the data. We only grab them from TiKV only once and calculate the FM sketch and send the NDV back to TiDB. And also there are only one hash function required. So we picked a really faster hash function from open source community, and we only have one hash function to calculate. It's really good. Because compared to original FM sketch, if you want to improve your accuracy, you need to use a different hash group to do the calculation. And after we calculate that FM sketch, I mean the NDV, we just get into the next part about how we're gonna do the sampling, right? Because we can send all the data back to TiDB. So here we have a very fancy algorithm because it's just the name is pretty fancy, but the implementation is so simple. So the algorithm is based on the assumptions. So basically, each sample in the data set is selected independently from other samples. And each sample is selected with a fixed probability across the entire data set. We will calculate a rate from TiDB side and send it to all the TiKV nodes. And the TiKV nodes will use this fixed probability to determine if we need to pick this sample or don't pick this sample, right? It's just like a Bernoulli distribution. There are only 2 results, pick or not pick, right? We just had give it a really fancy name. And to implement this algorithm is pretty straightforward. We just define a sampling probability P for selecting each sample. And we define it in TiDB it really depends on how big of your table. We'll calculate percentage, like how many data we need to scan from TiKV to build the TopN and build the histogram. And for each sample in the data set, we'll generate a random number and compare it to P. If the random number is less than P, we'll include this sample in the resulting set and send them back to TiDB. So it's literally the random selecting. It's just a fancy name. And this is a more detailed example of Bernoulli sampling algorithm. If you click this button multiple times, you'll see it's just a random sampling, right? We just sample rate is 0.3, and we just generate a random value for each implement and try to determine if this random value is less than 0.3, then we'll include it, right? That's how it works. It's pretty straightforward. And after we calculate the FM sketch and the sample data from TiKV, we'll send those like a subset or send those samples back to TiDB. So in TiDB, we perform the following things. First, we merge all FM sketch and the sample data because it's a data distributed system, right? We need to merge the result from all the TiKV nodes. And after that, after we merge them together, we can start to build the TopN and the histogram, right? And the last thing is after we get those structure in memory, then we can flash them out to the system table and prepare for optimizer using. We have already seen the data flow from TiKV perspective. Now let's just look at the data flow from the TiDB perspective. I don't really have enough confidence to say that I can really teach you how to the Analyze feature, because it's so many configurations control how the Analyze feature runs concurrently in TiDB and TiKV. And at the same time, the observability is not that good. I believe nobody can really master this feature. I think there is definitely a big room for improvement. Some names so bad, and I believe nobody can really get a clear idea what they do. You need to take a detailed look at those configurations. So don't worry if you don't really follow up or you don't really understand everything in my following slides. I don't understand everything either. So I'll try my best to explain the detail of the Analyze feature, but even for me, it took a while, almost 1 year, to understand how everything works together. So if you have any question about how to speed up TiDB Analyze feature or speed up the Analyze statement, you can take a look at this table and find which configuration probably will help you to speed up the process. So let's dive into the details. I'll explain each configuration and show the process in detail. This is a data flow for analyzing tables or partitions concurrently in TiDB. It's easy to understand. You can when we analyze tables or partitions concurrently, we can't just analyze them one by one, right? Because, for example, if there is a partition table, you can't analyze each partition or all of the partitions of this table one by one. That's gonna take a really long time. So for partition tables, we want to analyze them concurrently and try to reduce the overall time. And first, we will create we will create some tasks, analyze tasks for each table or for each partition. Because it's just a normal query, right? We still use that like a SQL interface. So it's we use the same framework to build the Analyze plan. So we use this plan builder to build the Analyze plan. And we'll start some tasks and start some Analyze workers for each task or for each table. And then we'll wait for the analysis completion. Once the analysis is done, we'll after we receive this analyzed result, we will update them into the system table. Write the TopN and the histogram to the system table as we saw before. But for the partition table, there is an extra work we need to do. We need to merge the statistic from each partition to generate the global statistic. Because right now, when we try to do the estimation or generate the plan for the partition table, we'll use a global statistic instead of the statistic from each partition. So we need to use the statistic we write into the partition table and grab them back to the memory and merge them together and generate the final global statistic for the partition table. The reason we don't just keep it in memory is that it's gonna consume a lot of resources, especially the memory. It's gonna cause some OM issue. So we decided to write them back to the system table first. Then we all have some more efficient way to load them to the memory and merge them like a piece by piece to avoid the OM issue. And finally, we will load the latest statistic into the cache to make sure the query optimizer can use the most up-to-date statistic to help you generate a better plan after we collect those statistics. And here's the first configuration called TiDB build stats concurrency. It's control how many workers we can spawn for the analyze different partitions and tables. By default, the concurrency is set to 2. And after, this is a big picture of how we analyze those partitions. But in this worker, we have some more detailed stuff we can dive into. So when we analyze a table or partition, right, we need to scan all the regions of the table to collect the statistic. So to improve the performance, we scan regions concurrently. So we still use the same framework of our current execution framework, right? We open this analyze executor, and it will spawn some co-processor workers to start scan the task for the different regions and different ranges, right? And then we'll wait for the result. And in these workers, we'll send the gRPC request to scan the region and get the data from TiKV. Once the analysis is done, once we get those information, we can build and merge the statistic and return the analyzed result. But here we introduced another configuration called TiDB Analyze disk-SQL scan concurrency. The default value is 4. So we all have a 4 worker to scan all the regions of one table. After receiving all the FM sketch, the NDV number and the sample data from TiKV, we need to merge them in TiDB, right? Because we scan them from region by region basis, right? To enhance the performance, we introduce another concurrent process. We merge the FM sketch and the sample data concurrently. So we'll create a root row sample collector. So this collector will combine all the statistics, all the samples from the different regions. And we'll start some workers and try to receive the result from the different region and merge them together to the root row sample collector. Once the merge is done, we'll build do the real work, build the TopN and the histogram and return the analyzed results. And this time we introduced another configuration called TiDB build sampling stats concurrency. So it's just for how many workers we can use to grab all the samples from different regions from TiKV and merge them together. This is another concurrency control. The default value is 2. And after we merge the FM sketch and the sample data, our next step is build the TopN and the histogram data structure in TiDB. The real data structure we will use in the optimizer. To enhance performance, again, we constructed the TopN and the histogram concurrently on a column or index basis. So here is the process. First, we sort all the samples collected in the root row sample collector after we merge them together, right? Next, we dispatch the build task for each column and each index. And we then initialize the builder worker and to start those work and wait for their completion. For each column and for each index, we'll build the TopN and the histogram data structure. And basically, we'll do some calculation and build those data structure in memory. Finally, after we get all the TopN and the histogram for each column and index, we'll return the final analyze results back to the executor to write them down to the system table. And to manage the concurrency, we use a configuration called build sampling stats concurrency. It's the same as this process. So we use this configuration. So this configuration decide how many workers you all use to merge the data you scan from TiKV. Also, it will control how many workers you use to build the TopN and the histogram for each column and each index. This is one example how we build the TopN. This build TopN is pretty simple, right? It's just a simple algorithm, and we just need to get the TopN values. Here, let's say we want to get the top 3 values, and the total count of this table is 200, and we only grab the 10% of this table. So the sample length is 23. So how are we gonna build the TopN? We'll start with for the first step, we need to sort the sample because it's gonna help us to build up grab these TopN values, right? So first we sort the samples we get from the TiKV from the different region, and we start to process each value. And because the current number is the current count is 5, and because we meet another 5, so the current count is 2. Then we put this value into the top list, and we will keep doing this stuff until we finish the whole sample data set, right? Every time if the current count is bigger than one of the top list element, we'll replace the orange one. So here, for example, the 13, we'll put it we put it in the top list. But if we meet the 200, because we have 2 of 200, so we are gonna replace the 13 from the top list. Then we get all the TopN from the sample, right? We just finish the whole process. Now, but after we build up this TopN list, we will remove those TopN values from this sample, because for the TopN, the main purpose is get the data skew of those values, because we already know the data skew of those values. So we don't need to just keep them in the samples and build the histogram based on the original sample. We can remove the skewed value because we already have that like a distribution information about these specific TopN values. And the next one is how we're gonna build the histogram, and we use the same sample data. And the total count is still 200. Because we already get top 3 values from the sample, we removed it from the TopN because we know that distribution of those specific values. So the sample length comes to 17, right? And to build the histogram, it's more like we need to build a range of distribution. We have as we saw before, we have a lower bound and an upper bound. It's kind of we use a range to represent the distribution of this specific range, right? Here, when we try to build this histogram, we need to consider the sample factor, because we do sampling in TiKV set. So every time we get a value, we need to apply this sample factor to get the total count we are located in this specific range, instead of just only include the whole data from the whole data set, right? And also because we want to maintain the equal head bucket, so we calculate how many values we can include in this bucket. For example, for this specific case, the per bucket count is 78. So we will go through the whole sample and try to fill up those buckets. Right now we only have 3 buckets, but in reality, TiDB will collect or build up almost 256 buckets. So it's quite a big number, but this is just a simple demo. So after we start to process those samples, first we pick the first element from the sample. So we all put it into the lower bound and the upper bound because right now we only have one element. But at the same time, you can take a look at this count because we apply this sample factor. So the count is 11, right? The low bound and the upper bound is same. It's 13, right? Next time, we just include another sample from our from the what we collected from TiKV, and this time because we still doesn't we don't really reach the limitation of per bucket count, so we just included this next value into this specific bucket and update the upper bound because we sorted the sample before, right? So we can keep this process till we match this. As you can see, we almost match this per bucket count. Then we move to the new bucket. We'll create a new bucket and set up the lower bound and the upper bound, and keep doing this until we finish the whole construction of the histogram. This is how we construct the TopN and the histogram in TiDB. You can take a look at the TiDB code. It's a pretty, it's a kind of a straightforward. But to understand the sample factor and the per bucket count and the other like NDV factor stuff is a challenge. You should take a look at the code base and try to understand how we build this histogram. Especially for histogram, it's a little bit complex. Finally, after we build the TopN and the histogram data structure, we save the statistic to the system table here. But to enhance the performance, we introduced another configuration called the TiDB Analyze Partition concurrency. So we basically spawn some workers or routines to help us to save the result we built up before. So the name is quite confusing because it's called TiDB Analyze Partition concurrency, but actually it's just responsible for the saving part. So it's a really confusing name, and yeah, it's really hard to understand. The default value of this value is 2. And for the partition tables, as I said before, we have extra work to do because for the partition table, we need to merge the statistic from each partition to generate the global statistic. But in this process, we definitely need to do it concurrently. So basically, we will start analyze the async global stats worker. And in this worker, we will start 2 different routines. One is the I/O worker, another way is the CPU worker. The name is quite confusing because for the I/O worker, we will load the FM sketch and TopN and the histogram from the system table. We already flashed them into the system table before during we analyze each partition. So this time I'll try to load them back to the memory like a better way because we can't maintain them in the memory for a long time. So we just load them one by one and load them in an efficient way. And for the CPU worker, it's basically do some calculation work. It's we need to calculate the FM sketch and combine them together and recalculate the TopN and the histogram in this CPU worker. But in this CPU worker, they only introduce the concurrency for the merge TopN for the global TopN statistic. And for others, like the FM sketch and the histogram, we just merge them one by one. And after we finished all the merge work, I mean, for the FM sketch, aka NDV, and for the TopN and for the histogram, then we can grab them together and write them back to the system table. But this time we will create a new record for the partition table for the global level instead of for each partition. And in this process, we introduce another configuration called TiDB merge partitions stats concurrency. So it's only for this part. By default, the concurrency is 1, so we literally merge them one by one. The analyze feature is critical. I mean, it's right now it's only input for the query optimizer to generate the better plan. but as you can see, it's really complex, and I think it has a lot of issues. If you are interested in the Analyze feature, you can track in the progress of the project in this tracking document. We are working really hard to improve this feature because it's pretty messy, right? And also, I just started a new series of blog posts to discuss the Analyze feature improvement. Hope we can deliver these features or improvements in the future. It's gonna significantly help us to improve this Analyze statement. All right, that's all for my talk today. Thank you for listening. Do you have any question? I guess there's no question in the chat box. I guess I'm pretty accurate because it's 11 a.m. right now. It's 1 hour.
Yeah, it's very clear.
Okay, cool. So if you have any question, please feel free to open your mic and ask me. If you have some question. Oh yeah, I'll share the PPT. Actually you can, let me see. If you scroll your mouse here. I didn't open that like a support feature. I'll open it after this talk, and you can download it as a PDF, or you can just use this to open this slide. But you can also export it as a PDF.
Okay, any other question?
Yep.
Okay. This sharing is coming to end. See everyone. Thanks for your participation. Bye.
Bye. Have a nice day.
Bye.